Euclid Book 1, proposition number 48. This is the last one in Book 1. When we do this again, we'll start with Book 2. Okay? So, what is the big deal about Euclid Book 1, proposition number 48? The problem is not proving the proof. The problem is drawing the proof. And I'll show you just how difficult this can actually be. And if you guys find a better way, you let me know, and I will do it the way you want me to do it. But I'm telling you, this is one of the most difficult proofs you've ever seen in your lifetime to make. Okay? Euclid wants you to start out with a triangle in which the two squares, which this is square A and this is square B, if you were to add the areas of both of these together, you would get the area of square C. Now, drawing squares A and B is no problem. I personally decided that just to kind of make it easier on everybody, what I did was I made a 1-inch square. Every one of these sides is 1 inch, right here. And then on this one here, I made a 2-inch square. So every one of these sides is 2 inches in length. The problem is making a third square, making sure it's square, but then having it a length that if you were to do the arithmetic on it, which I'm not going to do, but if you were to do the arithmetic, the area of this square is the combination of the area of this square and this square. Okay? Now, how do you do this? Okay. We're going to take the 1-inch square. We're going to divide it in half so it becomes a triangle. Okay? So this triangle is half of this. And then by using one of the previous Euclid proofs, and I know you'll recognize this when you see it. I think it's Euclid Book 1, proposition number 42. I'm not entirely sure, but I think so. You make this parallelogram here, which is the same area. The same area in this parallelogram is the same as this. Okay? And then you're going to use Euclid Book 1, proposition number 45. Okay? You're going to put this parallelogram right up here. And then what you're going to do, okay, is you're going to use the 2-inch length here, duplicate it here, as you can see here by using Euclid Book 1, proposition 45. You saw this being used in Euclid Book 1, proposition number 47, so don't tell me you don't know how to do this. And you're going to change the shape of this parallelogram to this. The area here is the same as the area here. It's just its shape is different. And what you're going to do is you're going to attach this area here to here. Okay? And then what you're going to do is once again use Euclid Book 1, proposition number 45. You're going to take this parallelogram here, place it here, and then you're going to have this area right across here, put right down here. And when you put this all together, this area here will be equal to the total of this area here and this area here. Now, if you have any better way to do this, I welcome you to leave that in the comments. Okay? But in the meantime, this is about the best way I could figure out to do this. Alright? And it took me 2 days to figure this one out, so if you have a better idea, I'm more than welcome to hear it. Let's get to the actual proof, shall we? Okay, we have a triangle here. As you can see here, it is A, B, C. And the square, now this is coming back to Euclid Book 1, proposition number 47. The square of this side and the square of this side is equal, if you put them together, their areas are equal to the square of this side. Okay? Now, we're going to draw another little line. This line AD is going to be equal in size to line AB. It's also going to be at right angles to line AC. Now, we didn't say that this was a right angle yet. We have said, however, that this is a right angle. That's all you really know at this point. Okay? Now, the square of AD, if you were to draw the square out here, is going to be equal in size to the square of AB. Now this is back in reference to Euclid Book 1, proposition number 47. Okay? So if you don't know what I'm talking about, you got to go back there. Alright? Now, you're going to add the square of AC to each. Now the square of AC would be right about here. Okay? I know you can't see it, but that's where it would be. Alright? So, the square of DA plus AC is equal to the square of AB plus AC. Okay? Now, DC, the square of DC right here, would be equal to the sum of DA and AC. Okay, the squares of DA and AC is equal to DC. And this is by Euclid Book 1, proposition number 47. We already said that the square of BC right up here is equal to the squares of BA and AC. That was given. So, by all of this and the transitive property, we can now say that the square of DC is equal in size to the square of BC. Alright? And so now we can also say that this line is equal to this line, and this line is equal to this line, and this line is equal to this line. So therefore, angle DAC is equal in size to BAC. Okay, BAC, DAC. And since we already said that this angle is a right angle, we can now say that this angle right here is also a right angle. And that's what we were supposed to prove. And that thus concludes Euclid Book 1, proposition number 48. And that also concludes Euclid Book 1, period. I will tell you more in a future video, so stay tuned.